Oh yeah, on the scattering as well. I've changed the end of this section in the light of a couple of comments that I've had. So I've just changed that a little bit. So please re-download the typed notes, and they won't match up with the handwritten notes perfectly anymore. Okay. The formulae at the end, which I'll show you in a minute, do actually agree with each other, but the way I'm writing it now is slightly easier, I think. Okay, so from here on in, hopefully, this is all groovy stuff. Okay. We're going to talk now. This is the end of section 4 today. We're going to talk about the scattering of radiation. Okay. So you can tell from my increased enthusiasm, this is. We had to go through the other bits, like the boundary conditions. That E over H thing, okay, relating E over H to the impedance was useful, as we shall see later when we look at guided radiation. Okay. Now, remember we said a couple of sections ago that if we had an incident photon, okay, which we took to be a plane wave and therefore had some kind of form where it had an electric field that was oscillating in time, when that was incident upon some charged object, say atoms or the electrons within them, that the acceleration imparted to the charge by the incident radiation gives rise to radiation of the charge itself. Okay? Okay, so an incident EM wave, okay, causes charges to accelerate, accelerate, and therefore they radiate. Very important. So we imagine in a situation where the radiated power is quite small compared to the incident power, that we can make an approximation that the transmitted radiation is nearly the same as it was before. We can do some kind of approximation for that. And we have the re-radiation which is scattered. This is what scattering is, of course. Okay? Now that picture is slightly wrong, isn't it? Because in our picture of an accelerating charge, the EM wave is coming along and it has a polarization, let's say it's vertical, which means these charges are being accelerated up and down. And you can see from this picture, it doesn't really matter which way around the radiation is coming from. Okay, I can draw any way up. Okay? So because from the point of view of the charges going up and down, it doesn't matter which way around the radiation is coming from, I should be getting radiation going off in any direction. I have no preferred direction. Okay? Right, so that's my statement about there being the radiation must be being isotropic. Right? So the radiation is isotropic and it obeys Larmore's formula just like we had before. Remember we did that derivation, which is generally true, that the power is proportional to the acceleration squared, right? And since we know that the intensity, the acceleration is proportional to the electric field, right? Okay, so the acceleration is proportional to the electric field, and the intensity is proportional to the electric field squared, therefore the radiated power is proportional to the intensity, which is kind of what you'd expect, right? Okay? So keep that in mind. So the more incident power I have, the more scattered power I have. That makes perfect sense. So let's look back at our atoms. So we're going to start by looking at atoms as we did before. And this is one of the reasons for going through that derivation for the power scattered by the change in light passage when you pass through a dielectric, right? So remember what we did before. We consider that atoms have bound electrons. Okay? So therefore, the electrons are being moved. Okay, so as the electrons are being moved under that force from the EM wave, okay, it creates a dipole moment. Right? Okay. And remember that dipole moment as a function of time, ignoring that retarded part. Okay, so we're going to. Sorry, why did I say that? No, it moves with time. It's equal to the charge of that electron times the movement it's had, which we saw was e squared over m, E0 cos omega t for some incident frequency omega. And then if that particular electron had a particular natural frequency omega 0 and some associated damping gamma, the solution for that dipole moment looked like that. Okay. So that's what we did in section 3. But now we see, quite obviously, from section 2, that this dipole, okay, it's going to radiate. And the important thing here, there's a few facts that we should keep in mind. Firstly, because the direction of the acceleration, the direction of that dipole moment, does not care which way round the EM radiation was coming over it. It only cares about the polarization direction. By symmetry, the dipole radiation must be isotropic. Okay, and it looks like, of course, a Hertzian dipole. Okay, and it emits the same omega, okay, as the incident omega, because the electrons are moving up and down at the same time that the electric field's going up and down. Okay? And the power, as a function of time, okay, goes as omega to the 4th. That's a very strong scaling. So if I double the frequency of the incident radiation, the power goes up by a factor of 16, which is enormous. It obviously depends on the overall size of the dipole moment that is created. Okay? And we have to take account of the retarded time between when the dipole occurred and when I'm observing the power at some distance encoded by t. Remember where t, the retarded time tau equals t minus r over c. So I just need to take account of that. But in a steady state situation, we tend to just omit saying that. And then we have the overall scaling formula, which we recall comes from that geometric argument of Mr. Purcell. Okay. Now, of course, I can just take those two equations, one for the dipole moment and one for the power for a given dipole moment, and I average out. So when I average out, okay, I get charge to the 4th, I get a factor 2 in the denominator, okay, from the averaging over time, and I just need to make sure I keep track of all those various constants, epsilon 0, m squared, and c. But the important thing is the scattered power goes as E naught squared, omega to the 4th. Those are my two important scaling values. It goes as proportional to the intensity. And then I've got the response of the atoms. Okay? So it's just like we had before. Great. Now, of course, I can describe the incident radiation in terms of the Poynting vector. Okay? So I should be able to relate. So the question is, can we relate, okay, the incident power, right, which is going to be S, to the radiated power, P? Obviously we can. We know they're proportional to each other. Okay? Right. So we're going to define that in the following manner. Now, I'm going to suggest that if this is a little confusing, what we're describing here is the concept of the cross section. Now, if you go to Lilley, Nuclear Physics, Lilley, okay, that's in the typed up notes. Chapter 1 goes through the concept of cross sections, and one of the key things that people get mixed up on is that root 2 for atoms. Don't use the root 2. Okay, so the example, there's a worked example at the end of section 4 that I strongly encourage you to look through step by step. I'm going to go through it now as well. Okay, but what we're doing is we're saying, I'm defining that the the electrons in the atoms have an effective cross-sectional area sigma. This is called a microscopic cross-section. So it's written as a little sigma. And you can see just by comparing units, if P is the radiated power in watts per second, right, and S is the incident power, okay, in watts per square meter per second, then sigma has units of meter squared, as it ought to. Yeah? So it's the effective size of the electrons with regard to how much they will interact with the incoming electric field and cause radiation. Okay? All right, so that's the radiated power, and that's the incident power. And so far, we're only talking about one electron. Okay? Right? So that power we wrote down above, that P, this is the power radiated by each and every electron when it sees an electric field E0 oscillating at omega. Okay. Right. And when we think about cross-sections, what you'll see when you look into this is that sigma can be written down in a variety of forms. So what we're writing here is sigma here is the so-called total cross-section. All right? What we mean by that is we're saying what is the chance for each bit of incident power, what is the chance that that bit of incident power is removed and re-radiated as radiated power, okay? Regardless of the direction it goes in. So we could subdivide that cross-section. We could say, what's the cross-section for radiation going forwards? What's the bit of cross-section for the radiation going backwards? But here we're just talking about all of it. It's the total cross-section. Okay? Which means radiated power in any direction. And of course, in the simple case here of isotropic scattering or isotropic radiation, right, we simply divide by whatever solid angle we have because it's the same in every direction. Okay? So we should just mention this is as opposed to differential cross sections, right, which you encounter very, very widely in physics, where we subdivide. Okay, subdivide that total into, you know, different angles, where of course here it's isotropic, different energies of photons, for example, and so on. Okay, very, very rich and wide area. Okay, so of course here the radiated photons all have the same energy, and they go uniformly in all directions. So sigma here is an area associated with the atom. Okay. So here the electrons are bound. So you can think of it either as being the effective area of the electron or the effective area of the electron with regard to the atom. The important thing here, it's an effective area. It's not this. Okay, it's the area. It's a number which arises because I'm thinking about the likelihood that a photon will strike that atom and cause a re-radiation. Okay, all right. So our concept here. So of course we can relate that area to the number of photons if we have a certain amount of power. So what the idea here is that the entire photon is scattered, okay, if we're counting photons. Okay, so if we hit that area sigma, the entire photon is scattered, and if not, then there is no interaction. That's our, okay, then there is no interaction. Okay. I'm just saying that it's the same thing a few times just to kind of, because I know this can be a bit fiddly to get the hang of to begin with. Okay? So what we're really saying is sigma is simply the proportion, okay, the proportion of photons which are scattered. Okay, so that's our kind of rigmarole to get us going. So P, power, which we can think about as number of photons per second. Slide up a bit more. Number of photons per second is equal to an area, which is in meters squared, say. Obviously it's a lot smaller than that, isn't it? Times the incident power, which can be thought of as being a number of photons per meter squared per second. Okay. Now, we already saw that we can write the incident power in another form. We can say it's half epsilon naught E squared, okay, the energy density times C, right? When we do that, we can write down the cross-sectional area. So this is the effective cross-sectional area which goes into that formula. Well, it's quite long. Let's write it out laboriously. 12 pi epsilon naught m squared c to the fourth. These are all the electron masses, of course. Okay. Omega to the fourth, because we've got rid of that electric field bit from that equation. Okay. Plus omega squared gamma squared. Okay. So all that bit on the right is just the same as it was before. Now that's a big mess of constants on the left. Can we do anything with it? Well, notice that a cross-sectional area, well, that's just a dimension squared. Is there an interesting dimension I can calculate? Well, let's call that R0. I'm going to leave some space on the left because I'm going to define what I'm going to call it in a minute. For some reason, which we'll see in a second, I'm going to combine some fundamental constants, E squared over 4 pi epsilon naught, okay, MEC squared, and it so happens that has dimensions of length, okay? And it turns out to be about 2.8 times 10 to the minus 15 meters, okay? Well, this is to do with radiation from electrons, and this is an effective size of those electrons for that radiation. This is all classical physics, so this is called the classical electron radius. Okay, and there it is. Nice important formula, that, obviously. And using that definition, the cross-section now is just 8 pi r naught squared over 3 times all that other stuff on the right. Okay, so we can say there's a size term and a term which depends upon the frequency of the radiation and the natural frequency of the atoms. Okay? So we'll see later why the 8 pi over 3 there. This R0 arises a lot. You can kind of appreciate, can't you, that a 4 pi is a kind of a nice thing to be putting in. It's got something to do with the electric field lines coming out from the electron. So that kind of makes sense to put that in there. Okay? And once you do that, then this cross-section comes out to be 8 pi over 3. Hopefully that makes you happy that it's done that way. The important thing is that the cross-sectional area is clearly proportional to the size of the electron squared. That should strike you as a really wonderful little equation. Okay? Now, notice that we're talking about electrons in atoms. Obviously, we're now going to start looking at some interesting cases. Okay? So our special cases are going to be subdividing into interesting situations which, from the look of that, ought to be frequencies. Okay? So let's look at the special cases. Okay? And we're going to combine them all together in a minute. Okay? So, low frequency. Okay? Well, the important number here is that, well, the important scale is that the incident frequency is much less than whatever those resonant frequencies are. Okay? So just to remind ourselves that omega zeros are the resonant frequencies of the bound electrons. Okay. Right. So if we do that, if we write down what sigma is in that case, we can make the approximation. It's got that same scaling value at the start, 8 pi r naught squared over 3, which you'll become quite familiar with shortly. And it just reduces to omega, the incident frequency, divided by the resonant frequency, whatever that is. Oh, to the fourth power, not to the square power, to the fourth power. Well, obviously, frequency is 1 over wavelength, proportional to 1 over wavelength, is proportional to 1 over lambda to the fourth. Okay. So this, I'm going to give it a subscript r. This is Rayleigh scattering. So the Rayleigh scattering cross-section. Okay? So put a little box around that. Okay? And the important statement here is that as omega goes up, in other words, as the wavelength goes down, the shorter wavelengths are scattered more, which of course you already know. You know this. But here we just calculated directly how much is scattered. Now, if only we knew omega 0, we'd be able to work out the exact power. Okay, but most of the time, all we really care about is the relative rate of scattering for a given type of atom. Okay. So a classic question one might ask is, if I had visible photons, okay, they're passing through air, and the air atoms have some resonant frequency which is much, much greater than the wavelength of the visible photons, or the frequency of the visible photons, then we can express the relative rate of scattering of, say, red photons to, say, blue photons. Okay? The relative rate of scattering goes as the fourth power of the wavelengths. Right? So let's put some numbers in. So the difference between the wavelengths of red and blue light is maybe only a factor 2 or so. Okay? So of course, to the fourth power, it's about 16 times difference. So that gives an illustration of that fourth power that we said was an enormous difference in the re-radiation. Okay? So the scattering and re-radiation is the same kind of idea. Okay? So obviously online, you can find plenty of pictures where you can draw the right kind of picture, and from this basic idea that if I have uniform white light coming from the sun, when I look at it, if I look at the sun at sunset, the blue light is scattered away, so sunsets are red, but in the daytime sky, the light passing overhead, the blue light is scattered more downwards towards us, the red light isn't, so the daytime sky is blue. Okay. Now, an important thing to recognise here important in several ways, is that in this scattering process, in this long wavelength scattering process, there is no net transfer of energy. Okay, so the atoms are giving rise to the scattering, but there's no net transfer of energy to the electrons. Okay? In other words, we call this elastic scattering. Right? And one consequence of that is that for each photon, the scattered photon energy is equal to the absorbed photon energy. Okay? All right. Now, next, what happens when we increase the frequency of the photons and we go near to that resonant frequency? Okay. So now omega is approximately equal to omega 0. Okay. So this is obviously what we call resonant scattering, as you might imagine. So we'll give it a subscript sigma res for the cross-sectional area. And now if we look again at that equation and we drop the insignificant terms and keep the dominant ones, we still have the same prefactor, as we call it. And now it has a different form with frequency because it also has this damping term that's become important. Okay? And it's important because this resonant scattering, this scattering cross-section is large because gamma is small. Okay? All right. So this is resonant scattering. Okay. So that's a phenomenological statement. Now, this is the fun one. high frequencies. Because we can say all sorts of interesting things about high frequencies, which we couldn't easily say about all the others. So here, the high frequencies, we're talking about atoms in which the incident frequency of the radiation is much bigger than any resonant frequencies, and also much bigger, okay, than gamma. Right? And then we see, when we look at that formula one more time, that the total cross-section, all the terms on the right just disappear. This is called Thompson scattering. This is the Thompson scattering cross-section. And we work out what that number is. It's about 6.652 times 10 to the minus 29 meters squared. Okay? What does this mean? It tells us, well, firstly we see there's no frequency dependence. Okay, so it doesn't matter what the incident frequency is, the effective size of the electrons is the same. And that's because as the radiation passes over the atoms, the electrons are being moved backwards and forwards more rapidly than any restoring force or any damping can act upon them. It's as if the atoms themselves aren't there. Okay? So that's why we introduced it this way round. We said, let's imagine our previous situation of a generated dipole moment, and we looked at those three situations, the long wavelength, the medium wavelength, and the short wavelength situation, this high frequency situation. This is the most interesting one, because of course here the atoms don't matter anymore. They're just electrons interacting. So whether or not you think about this cross-sectional area as being like an area of the electron or an area of the atom, well, it's the electrons that are doing the re-radiating, and here the atoms don't matter. So it doesn't matter if they're not there anymore. So this would be the cross-section that would apply if we just had electrons, if we had a sea of electrons, okay? Or an electron beam, for example, if the electrons are moving. We'll talk about moving electrons maybe some other time, all right? Okay? So this is, and you can see here that this Thompson scattering cross-section, well, we can replace all these other prefactors with sigma t. Okay? So we can write all the other cross-sections in terms of this one now. So this is the J.J. Thompson, isn't it? Right? So this is the Thompson scattering cross-section. Very, very important, obviously, because it says something fundamental about the interaction of photons and electrons, right? In our classical picture, which is what we do here. Okay? So Thompson scattering is the scattering, the electrons, put a column there, the electrons are free, comrade. Okay? Supposed to be bound in servitude to their atoms or something. Okay, so let's draw that out. So let's draw sigma. Let's imagine we still got our atoms. So here's omega, and this is sigma. So we have different regimes. So clearly around omega 0 there's got to be a maximum. Okay, so that's our maximum cross section, sigma max, right? And as we go up in frequency, the nature of that force that binds the electrons to the atoms doesn't matter anymore. I must have an asymptote here at the Thompson scattering cross section, and as I go down in frequency, eventually I'll get to my Rayleigh scattering situation. So here this is proportional to omega to the fourth. Okay, around the peak, okay, this has a width of the order of gamma. So on the left it's Rayleigh, okay, on the right it's Thompson, and in the middle of course it's resonant. All right. And just to finish off, clearly we can write the Rayleigh scattering cross-section in terms of the Thompson scattering cross-section with this extra omega over omega to the fourth bit on top. And I can equivalently write it in terms of wavelength as well. So if I have some kind of characteristic wavelength in the atom, I can calculate the Rayleigh scattering cross-section. Okay? It's kind of nice, that, isn't it? So, going quite well here. That's a bit of a romp through cross-section. Now, there's something wrong with this. Okay, we've seen photons scattering off electrons before, haven't we? Where else have we seen photons scattering off electrons? What other formula have we seen when a photon scatters off an electron? It had another name, beginning with C. Don't all shout out at once. Come on, someone shout it out. Come on. It's going to be me then. Okay, Compton. Yeah, you knew it was Compton. You just didn't like to say. Okay. So we've talked about photons scattering off electrons. That's Compton scattering. This is another one. This is Thompson scattering. They must somehow be related. How are they related? Okay. So in our original picture was the photon comes in, or some photons come in at a lowish frequency. The electrons are accelerated, and then they re-radiate. And this is remember, we've worked everything out purely classically. Okay. Our consideration of the electric field and the motion of the electrons allowed us to calculate the total power that was scattered, assuming that the total power scattered is small in comparison to the incident power. And again, this picture is wrong, isn't it? Because the scattered photons are equally likely to come back as to go forwards. Okay? So this is our incident wave. Right? We can equally well make that as a symmetry argument. It doesn't matter which way round the incident photons come in, the radiated power is the same. Great. So our basic facts were the scattered frequency, lambda scattered, equals the incident wavelength. All right? It's an elastic process. And we also didn't talk in any way whatsoever about the fact that that they were individual photons. I mean, we could count them up, and we could think of the photons and the electrons as having some kind of mutual effective area. That was our cross section. But we didn't say anything at all about their quantum nature, which is that they might carry momentum. Okay. So our statements about all the stuff above, the Rayleigh, the resonant, and the Thompson scattering, and of course the Thompson one is the most interesting one, isn't it? Those are the scattering of photons from free electrons. We assumed there was no transfer of momentum from the incident wave into the scattered wave. Okay? And clearly, in Compton scattering, that's not true. Okay? So Compton scattering is different. So this is our Thompson situation. Our Compton situation is that the photons carry momentum. And of course the crucial question is how much? There must be a crossover point where for a sufficiently small photon momentum, and that's obviously going to happen when the wavelength is long, that there will be no significant amount of momentum transferred from the incident wave to the electrons. Right? We can put a scale value on that. When does that become significant? It becomes significant when the energy of the photon becomes comparable to the rest energy of the electron, okay, which is equal to MEC squared. Okay, right. So you know, of course, that is 0.511 MeV. So that's our scale energy. So photons which are much less than half an MeV in energy are not going to transfer a lot of momentum. Okay. So what sort of photons are those? Well, obviously visible's fine. Okay, so visible photons of the order of 1 eV, even X-ray photons, which might be of the order of 1 keV. Those are more or less elastic, aren't they? They more or less carry no momentum. Okay. So even though there's in a free electron there's no net energy transferred to an atom because there's no atoms anymore, right? Compton scattering should be considered to be inelastic because I'm transferring energy from the radiated part, the radiation field, into the electron motion. Okay. All right. Now let's see if we can match those things up. This is where my notes are slightly different. So let me just pull those out. So I've just redone the buggers. If I can find the end my own notes. Give me a second. Where did I put them? We're running well ahead of time, so we've got plenty of time. There we go. Okay. There we go. Right. So. So the key figure of merit must be the amount of energy or amount of momentum that the photon carries compared to the rest energy of the electron. Okay? So we call this the recoil parameter. So let's give it some label x as is conventionally done, and it's equal to 4 gamma, the incident energy of the photon divided by the rest energy of the electron. Okay? And when we write it like that, now this is when you do quantum electrodynamics later, you can find out, you won't have to remember any of this, by the way, okay? I'm just trying to show you that there is a relationship between the Compton cross-section, the likelihood that the photon will interact, okay, if the photon energy is large, compared to the Thompson cross-section. So clearly when x is small, they should be equal. But when x becomes large, two things happen. Firstly, momentum starts to be transferred, so we expect the shape of the radiation field should change. It should no longer be isotropic. Secondly, as it turns out, the likelihood that the photons interact goes down. And it goes down, roughly speaking, as 1 over times the recoil parameter, 1 over the photon energy. Okay? And there's a whole load of other factors. Okay? But the important factor is that first one. Right? Okay, there's a few extra terms, and if you write it all out, okay, and there's some other bits which are in the notes. I'm not going to write those all down. Okay? The important bit is the very first bit. And when you work out all these other terms and you set x small, then sigma c, the Compton cross-section, is basically the same as sigma t. That's how we match those two phenomena together. Okay? So the Thompson cross-section, again, is when the photons do not carry significant momentum, and the Compton cross-section is when they do. Right? So how does that look? Let's try and plot that out. So there's a more accurate picture in the online typed up notes. Okay. So there's a couple of angles, and what I'm trying to show here is the vertical axis is the direction of the polarization, the electric field, and the acceleration of the electrons. So it's the same theta we saw before. Okay? So we know that the radiated power goes as sine squared of this angle. Okay? We should also write it down in terms of the direction that the photons are going in when they're incident, which let's say is from the left, for example. Okay? So it's pi by 2 compared to theta. So you need to have both those angles written down. Okay? Whereas the other direction, theta is pi by 2, okay? And the the photons are travelling to the right. So they, with respect to this axis, they're parallel to it. Okay? Now in Thompson scattering, as we saw, the radiated power, okay, went as like so. Okay? It doesn't care which way the electrons are going. Sorry, which way the photons are going. It doesn't care which way the photons are going. It depends on the acceleration. Now remember, that was a ring donut. That's not what is in the online notes. Okay? What we have to do is imagine I now had a beam of photons, which was here, this top picture is the polarized case. If the beam of photons is now no longer polarized, then that ring donut, I have to average it out over all those angles. Okay? Imagine taking several ring donuts and turning them over, it becomes a bit like a jam donut. Okay? So, same picture again, but now for unpolarized photons, I have to average out that Hertzian dipole around that photon direction axis, and now it just looks like a large lump. Okay? And the important thing is it's cylindrically symmetric around that direction. Okay? And it has equal intensity going forwards and backwards. And that's the important statement. That's a statement that there's no transfer of momentum from the photons to the electrons. Now, Compton scattering is different, and if you work out what that looks like, the basic idea here is, of course, is that because the photons are transferring momentum to the electrons, right, then we should get a larger rate of scattering in the forward direction. Okay? It's forward peaked. So we get more radiation going forwards than backwards. And that's the important statement. And so as the photon energy gets larger and larger and larger, that scattered radiation must be more and more in the forward direction. So here's some kind of intermediate situation where I have a significant amount of momentum. I think this one is for something like, I think it's like 1 MeV photons or something. Yeah? So 1 MeV photons, their energy is comparable to the electron energy, and I get more forward scattering. Okay. So this is the rate of photon scattering, it's not the energy of the scattered photons. So the other thing that's also happening, so in the dotted case, this is with the Thompson case, okay, the outgoing photons, their energy is independent of direction, okay, and it's also symmetric. With the Compton photons, two things are going on. And of course, the Compton formula you know very well tells you how the energy varies as a function of this angle. But what we plotted here is the rate of scattering as a function of angle. But they must all be tied together. Okay. So the stuff you should take away from this. This is just a finish off for today, and then we're going to start looking at guided radiation on Friday. So this is the end of section 4. The important things you should take away. Firstly, Thompson scattering is very important. Okay, it's clearly a fundamental process, and the important statements to make are that the scattering distribution is exactly the same, okay, as a Hertzian dipole, because it's the same physical process. Okay? Assuming that the incident wave is polarized. Okay? That's for polarized photons. Okay? And you can see here above, that's the difference, right? This is our Hertzian dipole for polarized photons. If they were unpolarized, I would smooth out over these different angles. Okay, that's the phenomenon that you want to remember. Okay. The next thing, of course, with Thompson scattering is we say it is quasi isotropic, which means that the intensity of the scattered radiation, okay, again for polarized photons, varies proportional to cos squared. Well, the way we've written it here is cos squared beta. Okay? In other words, like sine squared theta. Okay? Alright? And that's about as isotropic as you're going to get, isn't it? And the very crucial thing is the scattered radiation, because the electrons are moving along with that electric field in the incident wave, the scattered radiation has the same wavelength. Very, very easy to miss. When we go into section 6, that's going to be quite important, because we're going to start talking about relativistically moving electrons rather than classically moving ones. Okay. So that's the scattered radiation is the same wavelength as the incident radiation. Okay. And the other thing we haven't, it's kind of obvious, but imagine I had polarized radiation coming along and it's causing the electrons to move up and down. Because those electrons are moving up and down, the electric field they generate is in the same direction as their motion. Okay? So therefore, the polarization of that scattered radiation must be linear is linear and parallel, okay, to whatever the incident wave polarization is. Which I think I mentioned before, but it's worth saying again. Okay. And the other thing is that sigma, the proportion of the incident radiation, okay, which is given by sigma t, proportion of scattered radiation does not vary with wavelength in the free electron case. Yeah? Vary with incident wavelength. So that's a lot of important phenomenology. Okay? And remember that it's very interesting to relate this to the situation where the photons do carry momentum, which is Compton scattering, where they carry significant enough momentum to transfer it to the electrons. Okay. And then we have the following differences. Okay, the scattering distribution, in other words, which way the photons go and how many, clearly because of conservation of momentum, is peaked, as it's called, in the forward direction. As you might expect. And then the thing you saw at first year is the wavelength of the scattered radiation. The wavelength of the scattered radiation. Is generally larger than the incident radiation. The wavelength changes. And this is because of momentum transfer. Okay? And clearly, because it changes with angle, this gives rise to our familiar Compton formula. Well, this is the Compton formula now. We only had one before, okay? Now we've got a much better one, which is how many. Okay? Compton formula for photon energy. Okay? And also importantly, as I change the incidence, so rather than think about the outgoing, we tend to think of the Compton formula as the outgoing wavelength, right? But if we change the incoming wavelength, we expect that the proportion of scattered radiation goes down as the wavelength goes down. Proportion of scattered radiation reduces as lambda reduces. This is lambda incident reduces. Okay. Well, I haven't derived that. That comes from QED, which we don't do here. Okay. Now we talked about single photons all the way through. Okay. An important thing to look at is this example, which I'm going to show, but I'd like to work through it. It's in the back of the section 4 notes. Right? Which is what happens. So I think in one of the examples, you're basically asked to look through this, and there's a worked example in the example sheet. But try and just do it anyway. The basic idea is as follows. All the way through, we talked about one electron, and we calculated how much power is radiated by one electron if it's sat, on its own in a large vat of electromagnetic field passing over it. Okay, a large vat of photons. Okay. Clearly, we tend to have more than one electron in practical situations. So an interesting question to ask is, what happens if we have a set of those electrons, for example, in a plasma, and light is passing over that plasma, and it could be light of various wavelengths, it could be visible, X-ray, gamma ray, whatever. Okay. How much radiation is generated? Okay. And the important thing, and this is where you should look in Lilly to remind yourself how this works. If P, zoom in a little bit, P here is the power radiated by one electron, which has an effective area sigma, and S is the power which is incident upon it. Okay? If I have a number of electrons, the amount of power is merely proportional to the number of electrons, obviously. Okay? So I can do things such as this. Imagine I have a certain volume within which I have a certain number of electrons. Now total power is simply equal to, so here N here is the number of electrons per unit volume. V is the volume, so this NV is the number of electrons. I assume they're all seeing the same incident power. The power radiated from that volume due to this incident radiation is simply that. And that's all there is. Okay? You can make this statement as long as there is not significant absorption of this incident radiation. Clearly, if there is a significant absorption over some length, then S will change as a function of distance, and of course it should go down exponentially as the photons are absorbed. That's obvious, isn't it, right? Which tells you that if I have, let's say the number density, let's write that down just to finish off, the number density of the, put that here. If I have a number density N per unit volume and a cross-section area sigma, okay, then the likelihood that an incident photon will interact, it's conventionally written down like this: sigma equals little n sigma. Okay, so this is the cross-section of the little object, the microscopic one. This is the macroscopic one. So the typical distance the photon will travel is simply equal to 1 over capital sigma. Okay, this capital and little sigma is how it's conventionally written. It's annoying, but that's just how it is. Okay. Okay, so the mean free path is 1 over n sigma. Okay, so look at Lily. Lily will go through that step by step. Okay, so if you do have significant absorption, then the typical distance that incident radiation will travel is about lambda. If you're in a sea of radiating electrons with a number density n. Okay, but work through this case. See if you can explicitly calculate all the numbers in here. Okay. All right, so that's it. That's section 4 done. Guided radiation next, which you will hopefully love, and then the rest bit right at the end. All right. We'll fit it in fine. Just double checking. No. This is as far as we go. Yeah. Okay. So the two kinds of the resonant scattering, which is to do with absorption by the atom, and inelastic scattering is absorption of big photons by electrons. Yeah, basically. Yeah, those are the two inelastic processes. So we're really only talking about the phenomenology of Compton scattering here, none of the maths. Yeah, the Thompson scattering is enough. Yeah. Okay, radiation power. Okay.